Hello everyone, welcome back. This is lecture 8 of our computer vision course. Today we're going to introduce the deep image retrieval. We will introduce the idea of deep image retrieval itself, and then we will introduce how to reuse the features pre-trained in classification task for retrieval. And more specifically, we will introduce how to use the feature aggregation, embedding, and fusion, and then some of the fine-tuning methods for updating parameters in those pre-trained models. We already seen in the last lecture that deep learning is cool and convenient. We can create complex model or complex functions by just stacking layers. And the backpropagation can help us to update the parameters in an easy way. So that's the reason the deep learning, even the result of the model is complex. However, the training and testing are extremely easy. So it has been used for a wide range of applications. So today, we're going to introduce one of the examples, the image retrieval. The reason we're picking up the image retrieval is the same as previously when we're introducing the traditional method, because retrieval is a way to demonstrate how to use the features. And in deep learning, it's the same. We're going to introduce how to use the deep features in retrieval today. Here is the general framework of CNN we have introduced last week. Let's review it a little bit. At the very beginning, we have an input. It's an image, and we usually take each of the pixel as one neuron as for the input layer, and then it goes into the convolutional layers. Sometimes we are using the activation function to regulate the range of that result value. And then we probably use pooling and stacking them layer by layer. Those are convolutional layer. And basically, they are mainly for feature extraction. And the result is a set of feature maps. Usually, we flatten them as a feature vector and pass them into the FC layer, the fully connected layers for reference. And that part is in charge of classification. And then finally, we have the result at the final layer, given us the likelihood of the classification or over the labels. This is a general framework. In the framework, you could see from here up to here, the red line, the image have been already converted into feature vectors. And recall what we have introduced previously. As long as we can convert image into feature vectors, they will span a feature space, and in which you can conduct the image retrieval by comparing the similarity or distance between the query and the target images. And you can use the similarities to create a ranked list and display that ranked list to user. Then the image retrieval process is done. That is to say that we can actually use this part, I mean, a convolutional layers for feature extraction. Even it has been used for classification. However, we believe it can extract some representative features which are also used for image retrieval. So let's see how we can do that. First of all, we can reuse such kind of networks, and we would input our image into that networks, but probably we just take the result from the last convolutional layer. We may discard the FC layers in between, Then we can flatten the feature maps into feature vectors and project them into the feature space, where we can use the matrix to evaluate the similarity or distance between the target and the query. Then we can generate the ranked list. Compare back to the image retrieval to previous traditional image retrieval method, the only difference here is we are using different features. The feature space is now spanned by deep feature vectors rather than those in the traditional feature we extracted. And here is how it happens. We are actually replace this classification part with the retrieval part. You don't have to do, usually you don't have to do anything. It just reuse the network. Once the network has been trained for classification, we can use that because we don't need back propagation at here. The simplest way is just reuse the feature map. Every time you got input there, it's go forward path through each of the layers. Then it finally reached this final convolutional layer, and you got the feature maps. You flatten the feature maps into feature vector, and the rest of all is just the same as in the previous method. The process sounds simple and straightforward, and you don't have to worry about that. We're going to have a specific tutorial for doing this to use the pre-trained classification models for retrieval. I'll show the code, so don't worry about that. And at this moment, you can focus on it conceptually. To use the deep features is simple, but are there better ways, or they're the best way of using those deep features might be another question we have to answer. So can we construct better features instead of just using the raw feature maps? You might have that question in mind already, right? Yes, there are actually two groups of way. One is you don't have to do anything. You just summarize the feature maps after it has been extracted through the CNN layers. So we actually have introduced something similar in the last lecture. We're using them to summarize the feature map into compact and more representative layers. Like doing this, you can use the max pooling or average pooling by summarize those every consecutive windows into one neuron. So this is what we have introduced. You should be familiar with that already. So this is one way, and by summarizing them into compact features, it can speed up the process of image retrieval, and sometimes it even improve the performance by doing this. The pooling is easy, and in addition to that, there are actually another method we can do it, which is because every image has regions. Even in previous method, we are considering image as a whole. So we're taking the feature map as a feature. It's something like a global feature there. Not necessarily global feature, but you can consider them as global features. But remember, the images has regions. The different region represent different thing. So we could actually summarize those features by regions. In that case, we could have more details about that image. So this is the idea of our Mac. This is R actually stands for region. So what we're doing is almost the same as previous the pooling method. The only difference is we summarize them region by region. For example, we have different way of divide one image into different regions. We can do it, this is one region and this is another region. And maybe we can make smaller regions, like this is a region, this is another one. And we could use different combinations to create different regions. And for each of them, we can pull a result for that region. Then for an image, we have a set of results from different regions. Then those regions are like local features for image. And also we can do this for different channels, as we mentioned in last lecture. One feature map contains different channels, and we can actually do this for each of the channels. And that each of the channel also have a set of values. And so then we can concate those different values into one feature vector. And this feature vector will represent the information from different channel. And for each of the channel, we have some of the values representing the characteristics of that region. So it will be better by simply just pulling them. So that's the reason RMAC is widely used for as a method. We're using the feature map of those pre-trained classification models for retrieval. Very similar to that RMAC. RMAC actually are called single feed-forward pass because it feed the image into a neural network just once, and then it extract features from different channel and from different regions. However, there is multiple feedword paths. That means we can divide the image into sub-images there. And for each of the image, or actually it's a region, we can take that region as input for the neural network. So for each region, you will have a feature. And so multiple regions will be input into that network multiple times. You have several regions. You have several feature vectors there. And by doing this, you might get a more in detail feature vector there, because you have divided divided into them into different regions. So for either the RMAC, the single pass or multiple pass, you will frequently have the problem that for one image, you actually have several feature vectors there. It's not easy for retrieval, like we have seen in traditional feature extraction. So we have to summarize those multiple feature vectors into one single feature. And the BoVW, which we have introduced previously, can be used here. Let's review it a little bit. VLAD actually, for each of image, once we have several feature vectors, and we're taking a shift as an example here, you will see it's just several feature vectors there, multiple feature vectors there. We're using them to train a code book. In the code book, these are representative words by clustering usually. Then we assign each of them to one word in the code book. Then in that case, we can count a histogram about the frequency of each word. So this is BoVW method, bag of visual words method, for your reference, which we have introduced previously. And another popular method here is VLAD. I forget to mention that this can be used for the deep feature for sure, because the only difference is here we're substituting this part with the deep features. So for one image, you have multiple feature vectors there. And in VLAD, it's almost the same. So we have, again, we have multiple features for one image, multiple feature vectors there, and we construct a codebook almost the same as BoVW, and we do the assignment of each of the words to that in the codebook. But the only thing different is how we calculate this histogram. The histogram is calculated by something like for all the words with all the feature vector which have been assigned to one words, we will not count the number of feature vector which has been assigned to that words. Rather, we are count how each of the feature vector is different from that words. So we are calculating the difference. Here, this is the feature vector. This is a code word. So you will see by this function, which are actually membership function, see if this has been assigned to this one. So in this case, with that function, we are actually calculating average difference of these words. And for different words here, there are many other feature vectors have been assigned to there. We use this formula to calculate the average difference here as well. So in that case, we by repeating that for all the words in the codebook, we will have a VLAD histogram, which is actually corresponding to this part. It's very similar to BoVW, but it calculates the histogram in a different way. Okay, the last method we're going to introduce is the feature fusion. For method which don't change the parameters of the neural network. This is the last one, feature fusion, because different model have focused on different aspects of an image. So let's see, we have a model one trained for one classification task, and the other is a second neural networks which are trained for another classification method. We can actually just take the final result and concate them together as a feature vector. So in this case, this feature vector will focus on different aspects of that image. And we could use that for image retrieval. And this, you don't have to do anything. You just have you have 2 or 3 or more models there, and you have multiple feature vector. Just concatenating by concatenating them together, you have a new feature vector, which are probably more representative. Okay, we have actually introduced several such kind of method, which doesn't, in which you don't have to change the parameters of the original CNN or the pre-trained models. So this method are called off-the-shelf because you don't have to go inside to change the parameters. So by contrast, there are some methods in which you can actually update the parameters. And so by doing that, we call those methods fine-tuned methods because they're updating the parameters chain by the pre-trained models. And this is usually in the hope of by doing this, we can adjust the domain shift. The domain shift is something like this term actually has been used in a different scenario. For example, we have a data set 1, and so we have trained a model. So, but in the real application, we're working on data set 2, and these two are supposed to have some kind of difference. So by retraining that model on data set 2, well, the model will better adopt the characteristics of dataset 2. This is one type of the domain shift. So, but now we're talking about the retrieval. You can do the similar thing. The simplest one is, as mentioned, you can retrain the model in the new data sets. So, and those characteristics of the new data sets will be will better capture the domain. So what we're doing is we reuse the model, the CNN we trained for the dataset one. I put it here, and usually for dataset two, there are probably some other tasks are defined. So sometimes, not all the time, we will modify the FC layer a little bit. We will change the loss function a little bit there to adapt to dataset 2. However, after the training, those parameters at this pre-trained part will be updated, and it will be better for dataset 2. And at the same time, because the model is pre-trained, it actually has digest more samples there, and it will make the feature map more representative. Then by using the feature map, maps are more representative, is supposed to give us a better retrieval result as well. So after the fine tuning, we will take the feature map here for retrieval. And this is one method, the most straightforward one, which you can update the parameters for your image retrieval task. Another group of representative method for fine-tuning the parameter is called verification-based tuning. Here is one of the example. It's called Siamese network, which means we have actually two streams, as you have seen here. There is an upper stream and there is a lower stream. So for this two stream, it starts with a convolutional network. Pre-trained. Those could be those pre-trained for a classification task, and the latter layers are FC layers there. But for updating the parameters, we are using a specifically designed loss function. The idea is every time during training, we input a pair of images. So yeah, like here we have XA, we have XP or XN. Anyway, every time we either input a pair of XA and XP, P here stands for positive examples, or we are inputting XA or XN. N stands for negative examples. So when we are input the negative pairs and when positive pairs, it goes here. One image goes here and the other image goes to here. So we know because they're positive means these two images are related. For example, if we're looking for dogs, if both image contains a dog, then it's positive pair. We will make the final output. We will hope the final prediction will be 1 because they are relevant to images. Relevant. Let me rewrite it in a better way. Relevant. And so we hope the output will be 1. And in case we are inputting a negative pair, for example, the query image is a cat, which goes to here. The target image is a dog, or vice versa. This is a dog, this is a cat, as shown here. So in that case, it's a irrelevant pair. We hope the output will be -1 or 0 sometime. So by doing this, you see we are actually comparing two images every time. When they are relevant, the output is 1. That means they are relevant. And when they are irrelevant, the output is -1 or 0. And this can be considered as the labels, ground truth labels for that training. So with this setting, the neural network is doing the class prediction. The only difference is we have this is binary classification problem to distinguish the relevant pairs from the irrelevant pairs. Then everything goes back to the classification. Um, this will enable us to do the retraining, and during that, the weights of the original CNN layers will be updated in between, and we are actually construct neural network specifically for retrieval. This neural network can help us to compare two images to tell us they're relevant or not. Because in image retrieval, we are basically trying to find the relevant images for a query. So again, let me summarize. For any time at runtime, you have a query. After network has been trained, the query goes to here, and from the dataset, you can take each of the image from datasets as a target, and the target goes to here. Then this neural network will tell us it's relevant or not. That's a prediction of this neural network. Then you can use a classification framework for retrieval. Then you can create a rank list based on the prediction. So that is the idea. And this is indeed what the loss function is telling us. And the loss function is trying to push the final feature representation in the feature space more closer together, and also at the same time to exclude the irrelevant images far from each other. So this is the idea of verification-based tuning. The reason it's called verification-based tuning is we are actually verified they are relevant or irrelevant, those two images. There is another set of methods which are also very popular, but based on the similar idea called triplet network. The triplet network has 3 streams this time. So every time you have to input 3 images, something like you have a query as the first one, and you got a positive example. That means the relevant example. And at the same time you have a negative example, and basically it's irrelevant one. So every time you have 3 images as inputs, and the structure is very similar to the previous one, except we have 3 streams. And then finally, you're trying to make the first 2, because they are positive pairs, more closely distributed than the latter 2, because I'm sorry, it's not the latter 2. The first one and the last one. So there are actually 2 pairs very similar at this previous 2-stream network, but the idea is very similar, except you can train once. You don't have to do it separately, because for that you need a lot of pairs there for training. But in Triplet, it can be done once and also at the same time, you are actually referring to both relevant and irrelevant samples at the same time. So hopefully it will be better for you to train that neural network, and better for network to be the learning process to converge. So Triplet is neural networks are really popular there in verification-based tuning. However, even those triplet networks are popular and makes a lot of sense, but you might have seen that you still need the ground truth to tell they're relevant or irrelevant there, so you can conduct the training. That group method also falls into the supervised learning method. By contrast, there are actually another group of method which can use the unsupervised learning to do the very similar thing as the triplet. To begin with, we have to introduce the manifold learning. Manifold learning is something it's an unsupervised method. Given a set of samples there, the manifold learning will learn something, actually learn a new space. In the new space, the feature vector which are close to each other. For example, in retrieval, we can see that the relevant samples were distributed more close to each other than those irrelevant pairs. So simply saying, you could think of the manifold learning that way. So with that learning method, we can see that this can naturally help us to figure out the relevant pair from irrelevant pair. For example, if we are looking for one relevant pair, we probably will pick up the pair from here. If we are looking for some irrelevant pair, we can take one from here and one from here, just for example. So this is a method, you will see this is a method can help us to pick up the samples. And for those samples, we have a pseudo ground truth label. So because it's pseudo, even it's pseudo, but it can be generated automatically. So you don't have to do the labeling by yourself. It saves a lot of efforts. So that's the reason it can be used for doing the fine tuning. Let's see how it happened. So here, this is an iterative process which can help help us to do the triplet training using the manifold. So what's happening here is we have some of the feature vectors here already, and we go the manifold. The manifold, as I have shown previously, can propose some of the pseudo pairs. I mean, the relevant and irrelevant pairs there. So we can use that pseudo label to do the training, to train the triplet network. Then after that, when the model is trained, it outputs some of a representation, and this representation actually span a new space of, and which the representation are new feature vectors as well. So we can, based on that feature vectors, we can go manifold for again. In manifold, propose the pairs, retrain net neural networks, and then generate new representation or new set of feature vectors. And we can go this iteratively, and hopefully the manifold learning and the deep neural network learning will help each other to find a better representation at the end. Then the final result of the neural network, you can use it for generating representation for image retrieval. So this is the idea of iteratively and unsupervised fine-tuning methods, just for your reference. And actually, due to the time limitation, we cannot introduce all the methods for deep neural network, deep image retrieval. Actually, there is a survey you can look at, and there are basically, as I have introduced two grouper methods, one is off the shelf, in which you don't have to update the parameters, and then another is fine-tune method in which you update the parameters of pre-trained neural networks. And there are actually a lot of methods already. And if you are interested, go check them out. Okay, thank you very much. That's all for today. Today we have used the pre-trained classification models for image retrieval. I hope you enjoy. Thank you very much.